In 1921, Paul Dirac developed, with the addition of the theory of relativity, a relativistic theory for the electron, but without taking into account the interactions between the electron and light. He established that the magnetic moment of the electron had to be exactly 1. Experiments then showed that the value of this magnetic moment was 1.00118. So as people knew electrons interacted with light, this little correction had to be solved with the addition of light into the equations. But bam! The theory resulted in nonsense and resulted in infinite. The problem was then solved by Julian Schwinger, Shinichiro Tomonaga, and Richard Feynman around 1948 with a theory that is known as quantum electrodynamics, or QED for short. The theory takes into account the motion and interactions of electromagnetic forces. Schwinger was the first to solve it with a result of 1.00116, closer to experiment. Finally, there was a theory that described electrons, and with wonderful accordance with the experiment. Actually, Feynman called the jewel of physics this experiment, since it predicted results with accordance to experiments with amazing precision. Now, all three got the Nobel Prize in physics for the theory, but Feynman's formulation is the easiest to understand, because as you might have heard, he developed a series of pictures called Feynman diagrams, which is gonna be the subject of this video.
So hi, my name is Ricardo Barbanera, and so these Feynman diagrams, okay? Feynman diagrams were this amazing idea made by Richard P. Feynman, notice the same name, that helped explain intuitively the famous theory of quantum electrodynamics, or QED for short. So he postulated three basic building blocks for the theory, as you can see. So we come over here. First, the first postulate said that a photon goes from one place and time to another place and time. The second postulate says that an electron, and the same, goes from one place and time to another place and time. The third one says that an electron emits or absorbs a photon.
Hello, my name is Cesar Gonzalez, and to continue what my colleague Richard was saying, Feynman also came up with a mathematical shorthand for these actions. Let's go. There were three actions that you need to take. First, from P from A to B. Secondly, E of A to B. And thirdly, just a number J. All of these are called probability amplitudes, and to find the probability of the action to actually happen, you take F of A to B and just square the absolute value. The basic rule of probability amplitude are that if an event can happen in a variety of different ways, just sum each of the probability amplitudes of the possible ways. And secondly, if a process involves a number of sub-processes independently, then you take the product of the component probability amplitude to get a resultant probability amplitude. So with these rules, you can solve any complex photon, electron, interaction fitting together the actions and rules.
So these actions, as you might have suspected already, have a pictorial representation, Feynman diagrams. Let's take for example one of the most basic collisions, two electrons colliding together. First of all, we have to remember that electrons and photons come in discrete chunks. So the idea goes as follows. Two electrons approaching one another, then one of them emits a photon that hits the other electron. Then both recoil with the standard energy momentum physics. We can draw a Feynman diagram that does exactly this. Here, the straight lines represent the electrons, and the wiggly lines represent the photons. As we can see, this is a quantum field theory book, and it's good to know that this is not the only Feynman diagram that there are, but there are a variety of diagrams.
One thing to note is that every time a photon interacts with a charged particle, the chance of this happening becomes less and less likely by a huge difference. For example, a single extra photon emission drops the probability to 1%, while two emitted extra photons drop the probability to 1% of the 1%, giving you a 0.01% of probability. So the really simplest Feynman diagram is also the most important one.
Hey, hi, it's me again. So now we're going to return to our example of the electron-electron collision. Each symbol of the Feynman diagram corresponds, as we know, to an action that translates to a probability amplitude. Here I'll explain each one. So here we have object, diagram, and symbol. For the incoming particle, which is depicted by a straight line, and the outgoing particle, which is depicted again with a straight line, it's gonna be or I or U or U bar. For the outgoing particle, it's gonna be an O or B or mu or nu or nu bar SR. This corresponds to the four-component column of the row spinors. We're gonna put it right here. It's gonna be like that. U bar SR SR. It's gonna be the column, the four-component column or row spinors. Now I'll explain the photon, which is depicted by the wiggly line. Here essentially we have minus I G of mu nu over P squared. Where I'm gonna put where G of mu nu is the Minkowski, I don't know, metric tensor. And P is the four momentum of the virtual photon. Now the vertex, which is depicted right here, corresponds to minus I e to the gamma mu, where the gamma to the mu is going to be just a set of 4 by 4 constant matrices. And you know, I and it's gonna is the imaginary number, and E, it's Euler's number.
So now we are ready to stitch things together. We can draw the simple Feynman diagrams and immediately write the equations. We color-coded the symbols so you can see how they come together. For example, the green arrows goes with this part of the equation, the red vertex goes with both of these, and the photon goes with this part.
The genius of Feynman is that each drawing has a corresponding equation, so you can imagine all the possible diagrams and the equations come for free. When you get really into it, you understand the power of this tool, so go into physics.